Hello! Today we are going to look at how we can optimize Hutton's Razor. So you might remember from the last set of videos that Hutton's Razor was this small language of expressions. So we had the untyped version and we had a typed version, which I'm going to use today because it's easy to use. We have numbers, booleans, addition, and if then else. Right. And now we would like to optimize these expressions in different ways. So here I would like to implement so-called constant folding, which is the idea that if you have two numbers that you want to add together, then you might as well do it before you compile the program. So instead of doing 5 plus 4 in the compiled code, you might as well do it before you write the machine code. So we do this by pattern matching on the expression, right? Okay, so for a number, we have no choice, we just have to return that number. If it's a bit, we just have to return that bit, but if it's a sum, then this is where we actually want to do some work. Right. So here, we would like to look at these two sub-expressions and see if they are numbers already or not. And if they are, we want to replace the whole thing with just a number, so we don't have to do this addition anymore. Right. So we do that with a with. And then it's tempting to just look at e and e prime, but remember that we also want to go inside these terms and optimize these, because that might in turn expose some further unfoldings. So we really want to look at c fold of e and c fold of e prime. Right, that's easy to forget. Otherwise we would stop at the outermost layer. Okay, and then the interesting case is if these things actually are numbers, right? So these are m and m prime, then we have to do something. And if not, this is some constant folded e, and this is some constant folded e prime. Right? Then there's probably not much we can do. But these are the two cases we're interested in. They're either both numbers or we don't care. Right? Okay, so if they are both numbers, then we can replace this with just one num, where we add them together here at optimization time. So note that this is really a semantic plus, not one of these syntactic pluses, right? Okay, and otherwise we have to keep the syntactic plus, and we just use the two optimized expressions which we already computed. Right? If it's an if then else, then all we have to do is we have to go into these different sub-expressions and optimize these. So it's if c fold e, then c fold e prime, else c fold e double prime, right? Okay, so that type checks, and let's try to run it. So here in lectures Hutton we had some example expressions, te1 for example. So if we look at that, te1, we see that's num7 plus num3 plus num5. So if I now look at c fold of te1, you see that that has turned into just one num15. So we saved two addition operations at runtime by running this optimization. Okay, so in the next video we're going to show that this is actually correct. But already now we can see that it's at least type correct, right? Because the very type of c fold promises that if the input expression had type t, then the output expression also has type t. So we haven't changed numbers into booleans or something like this. But we still haven't ruled out that we have changed everything to 17, for example. Except that would not work for all types, I suppose. But we don't know that the meaning of these things are the same, so that's something we can prove in a later video. But for now, let's just summarize what we've done. Well, we optimized the expressions by just implementing this function, which was quite pleasant by pattern matching. And the one pitfall is that it's easy to forget to also optimize these recursive calls. So that's something we have to remember to do.